Okay, welcome. I'm Francois David. I'm happy to be here again this year. Discover new faces and new brains. My course, let me just introduce myself. I'm a theoretical physicist from France, from the Institut de Physique Théorique, which is a large institute of theoretical physics south of Paris, in size, in number of permanent staff and of students, and it's about the same size as the Perimeter Institute, but not in such nice and new building. But we survive. Okay, and well, if you have any questions and want to discuss with me, I'm here for the 4 weeks of the course, and my office is just down there, so don't be shy and just see whether I'm available or make an appointment, but you can come. If I'm not at the seminar, I'm not busy with something, we'd be happy to discuss with you. Okay, so I'm happy also to be working with Dan once again. Okay, so let me now first to try to explain what I'm going to do. So I'm supposed to do quantum field theory 2, which is supposed to be the continuation of quantum field theory 1, but also of quantum theory. And so I looked a bit of what has been done in the previous lectures, because some lectures have changed. And I'm trying to adapt a bit, but so let me just explain the purpose of the course, or at least what I'm trying to cover. So this is QFT2. So I put Dan and Gang explain why quantum field theory is needed to do physics. They introduce you to the canonical quantization formalism. Basically, what you can do is using interspace, states, asymptotic states, scattering, calculating scattering process. And the purpose of this course is to go deeper in the formalism by discussing basically 3 things. First, I try to introduce path and functional integral quantization. So I've been told you had an introduction to path integral quantization by Feynman path integral in quantum theory, but I don't know exactly how far you went. Maite just gave me a few snapshot, a few keywords. So, but basically I'm going today, and then for the beginning of this lecture will be devoted to reminders of path integral quantization, and then applying that to quantum field theory. Then it becomes functional integrals, because we deal with functions or fields rather than histories of particles. So this will be used basically for the free field, the free scalar field that you have studied in QFT1, and also to develop the theory, or to redevelop the theory of perturbation theory. And Feynman diagrammatic. That you have been introduced, I think, in QFT1, but also I think you have seen some Feynman diagrams in the statistical mechanics course. So, but, okay. So this will be done basically on the example of the scalar phi-4 theory, which is something that you've probably seen already in a different, maybe under a different name in the statistical mechanics course. Okay. So the second, then well, a side step of prime is going to apply functional integral quantization to fermions. Okay. The second part of the course will be devoted to renormalization theory. So an introduction to renormalization. So I presume you have been learned a bit about renormalization theory in the context of statistical mechanics by Pedro Vieira, and I presume you discussed already the necessity of renormalization in QED at one loop. So we are going to discuss that, but more from the point of view of functional integral quantization, which allows to make the connection between renormalization theory in high energy physics and in statistical mechanics. Okay, and finally, well, that's a big part, but which is an introduction to non-abelian gauge theories. It's going to be only an introduction because it should be a full course or 2 courses devoted to non-abelian gauge theories, but you are going to learn more in the more advanced course. Okay. Okay. So I don't know exactly how this will be organized in time, except that I'm going to treat this, I presume, I hope so, after this, because it's a bit disconnected. So I understand that this year the course is over 4 weeks. So I don't know exactly which course, but this will probably be clearly the first week and possibly the first, the first part of the second week. And then we'll see. Okay. So any question or comments? Okay. Oh, of course, don't hesitate to ask questions during the lectures. Don't wait for the end of the lectures. Okay, so let me start by path integral. And okay, maybe I'll start not by path integral, but by something which is going to be important. So this is one path integral. In quantum theory. And so this is the first part of the course. And let me first not discuss path integral, but do a bit of abstract nonsense by discussing what is quantum mechanics in real and imaginary time. So, presume you have heard already about Euclidean time and real time, possibly in statistical mechanics, and I need a bit of formalism. It's going to be important when discussing functional integral quantization. Okay, so let's start from the simplest textbook quantum system, which is one particle, non-relativistic, with a mass m, no spin. The speed is much less than c. And in addition, in one dimension. So basically, you have a space which is one-dimensional. The position is labeled by q. So p will be the momentum. And the action, the classical action for the particle S is just the integral over time of m over 2 q dot squared minus v of q, where v is a smooth potential. So there is some potential living in the. So it can be an harmonic potential, but it can be a more general potential. And of course, q dot is dq over dt. That's the velocity. Okay, and the classical momentum will be P equal M Q dot. Okay. Okay, and so you know that when you quantize this theory, well, you have to use Hamiltonian, quantum Hamiltonian, H, which is P squared over 2m plus V of Q, where P and Q are now the quantum operators. Okay. So which satisfies QP equal I H bar. And a state is a state, quantum state is described by a ket, which is an element in the Hilbert space of the system, and the wave function psi of Q is just the scalar product of a position eigenstate Q with a ket psi. So this is the ordinary wave function, which obeys the Schrödinger equation. Okay, and therefore the evolution, the quantum evolution of the system of the particle, is described by an evolution operator U, which is an unitary operator, which is defined by, it defines the evolution of the system from an initial time Ti to a final time Tf. Initial, final. And since such an Hamiltonian is time independent, that's just a simplification. It can be generalized to time-dependent operator. The evolution operator is just E. Where is E? It's not even written here, but T over I H bar times the Hamiltonian, where T is T final minus T initial. So this is what I'm going to call, in fact, the evolution operator between the initial time Ti, or let's Tf. That's what I'm going to call U of T. Okay, and this evolution operator is just states that if at time T high the system is in state psi high, initial state psi high, then at time T final, it's at time psi final, which is U of T psi initial. Okay, and you can check that from this definition. You check that psi f, the dependence in Tf of psi f obeys Schrödinger equation. Okay, and of course all this picture is in the Heisenberg picture. Okay, so that's just textbook quantum mechanics. Okay, so now I'm going to do a bit of, math by stating that, where is it written? Yeah. If your particle is living in some bounded potential so that it has a discrete spectrum, things are just a bit more complicated in the case of a system with a continuous spectrum, like a particle in the plane, but so that's just for simplicity. So if you have a discrete spectrum, well, here you are going to have, so if you have a discrete spectrum, for the Hamptonian. Namely, you have eigenstates. Let's label them I, such that Hi equal EI I. This is eigenstate. And energy eigenvalue EI, which is such that E0 is less than E1, less than E2, etc. So that 0 is a ground state. Okay. Then, of course, you can write this evolution operator, U of t, in this basis of eigenstates of H as sum from I equals 0 to infinity of E t over I H bar EI. Well, we have two i's, so let's label them A. Times the projection operator on the one-dimensional subspace generated by I. So it's just a diagonalization of U of t. And then, I'm sorry, that's A. In my notes, it's I, so I just decided. Okay. And now you can do a bit of abstract math and ask what's happening if t is complex. Okay. And you see that as long as imaginary part of t is negative or 0, U of t, defined by this formula, is well defined as a bounded operator on the Hilbert space H. Well, the standard Hilbert space of square integrable functions on the real axis. Okay. Bounded means that what is a bounded operator? It's a very important mathematical concept in the theory of algebras of operators and acting on Hilbert space. And a bounded operator is an operator, let's call it O, is bounded if you can show that for any psi this is bounded by some constant for any non-zero vector. Okay, is bounded. And you see that since the series of e's is growing, so as long as t has a small imaginary part, which is negative, then this number decreases with t. So the series is convergent in the space of operator with this norm. In fact, this defines a norm. This defines what's the norm of the operator squared, and this is less than infinity. So this is a definition of a norm of the operator O. And the fact that we have to take O dagger O means that this is a positive self-adjoint operator. So O doesn't need to be self-adjoint. It can be unitary like that, or it's not unitary. Okay. So, but of course, this fails if the imagined part of t is positive. So basically, this sum is infinite. This series gives an infinite result, so it doesn't make sense. So you can view in a bit of abstract way. So this is the axis of time, real-time axis. Okay, now you think of this operator as defined in a complex plane. Okay. And then, so this is the axis of imaginary time. It's a mathematical concept. And you see that this infinite series defines an operator which makes sense in the lower half plane, with boundary, the real axis. So u of t is well defined here. Half plane. Okay. And not only it is well defined, but in fact, if you think about it, you see that each element is it's an exponential. So it's an analytic function. So you can make, if you work a little bit the math, you can see that u of t is an analytic mapping of the lower half plane onto the space of the, let's call it B of H, which is a space of bounded operators. Okay. Okay. So this is a very simple remark. Okay, so in fact, the evolution operator is defined as a function of t in the whole lower half plane. Okay. And in particular, something interesting happens when time is purely imaginary. So when time is purely imaginary, so this is my second blackboard, so let me write this the third blackboard. This was the first blackboard. Then what's interesting is what happens if what we call Euclidean time. So what's happened if time is minus I times some variable tau, where tau is real and positive. So we are somewhere here. Then, of course, u of t is just exponential of minus tau over h bar h. So it's just the exponential of minus some factor times the Hamiltonian. Okay? And then, so it's a self-adjoint positive operator. Okay? And we are going to consider this, this real variable tau. We call it, by definition, Euclidean time. Okay. And I'm going to call back to go back to this denomination just in a few minutes. But before that, and then I'm going to write this as UE, the subscript E for Euclid, Euclidean of tau. So this is equal to UE of tau. So this is a Euclidean evolution operator. Okay, it's just a label, a denomination. Okay, so then Well, there is one important but somehow simple remark, which that if you go back to the statistical mechanics course, in statistical mechanics, you know that in general, a classical system in statistical mechanics is described by the density, a probability density distribution in phase space, in classical physics. But in quantum mechanics, in quantum system, if a quantum system, you study it from the point of view of statistical mechanics, so you don't know exactly in which precise pure state it is, but it is a statistical mixture of pure states, then it's in a mixed state. So a quantum system, a quantum mixed states is described by a density matrix. Okay, so density matrix is a positive matrix rho. So it's a matrix, it's an operator, and its trace is 1. So this is the analog, the quantum analog of a probability distribution in classical physics. Okay, and that's a very old and important concept of quantum physics, because it goes back to the 30s, to I think Landau, von Neumann, and Bloch. So it's a very old, one of the first important concept that came out in statistical mechanics, in quantum physics. Okay, and so this is a general statistical state of a quantum system is described by a density matrix. But an important states are the famous Gibbs states, which describes system at thermal equilibrium. Okay, so which in quantum physics is somehow the same thing than in statistical physics. If you imagine that you have your small quantum system, which is small, and it's in contact with a very big thermostat, so big. And it is at equilibrium with the thermostat. Then, if it is at equilibrium, then everything you need to know about the quantum system is its temperature. So a Gibbs state is characterized by a temperature, T. Okay? And you know that the probability of being in a specific state is given by a Boltzmann weight, which is the exponential of the energy divided by the temperature. So, in quantum system, the Gibbs density matrix is just the exponential of minus beta times the Hamiltonian divided by normalized by the trace of exponential of minus beta h with beta equal 1 over Boltzmann constant times the temperature, as in classical mechanics. So that's the quantum analog of the Gibbs state. And I think in the statistical mechanical course, Pedro, you discussed more why there is thermal equilibrium in simple quantum system, and he showed you some numerical experiments showing how this happens. So, of course, the theory of thermal equilibrium and what is the concept of temperature when you have a quantum system in contact with some bigger quantum system. It's a highly non-trivial theory, in fact. The theory started in the 30s with von Neumann, Landau, but it's still going on. Anyway, I just need that. And, okay, because I need that because, oops, simply now, we can make the very simple remark, the following remark. So, of course, when you have a quantum system, you have also what's called a partition function. Okay. And the partition function of a system is just, it's a function of the temperature, and it's just the trace of exponential minus beta h. With this important relation. Okay, so it's a trace of the exponential of an exponential of h, and of course this looks very much like this. So basically, you see that you have a mathematical analogy, which is both, trivial or very naive, but in fact important physically, which is that exponential minus 1 over kBT h in quantum statistical mechanics is very analogous to this Euclidean evolution operator. So this is the same thing than UE of tau with, of course, tau over h bar equal 1 over kBT. And that's a very important relation. We are going to discuss that a bit later, but you see that basically Euclidean time can be viewed as the inverse of a temperature. And moreover, Euclidean time is h bar divided by the temperature. This is just a normalization factor that defines what are the unit temperature. So tau is h bar divided by t. Okay. And therefore, the partition function z of temperature is just the trace of the evolution operator, Euclidean evolution operator, with tau. With this tau related to t, this Euclidean time related to t by this relation. Okay, so of course this is a partition function for a system in a Gibbs state. So this analogy is restricted to quantum system at finite temperature in thermal equilibrium. As soon as the system is indifferent, it's not at thermal equilibrium, then this analogy breaks down. There are generalizations, but so this is very specific to Gibbs states, but that's important. Okay? Okay. Any question? Okay. So
I have a question.
yes?
So is there, this works mathematically, but is there any physical interpretation to what this means?
I'm not sure. Well, I'm mathematically inclined, so I tend to think of this both as physics and mathematics. But there are cases where you can relate this tau to a temperature, for instance, in black hole physics. But you should keep in mind that it's a dictionary. There is no direct interpretation. Because the temperature is a somehow very subtle concept. It's something that emerged from the, from thermodynamic theory, thermodynamics and statistical physics. It's not something that you can think of something like space, or which for most of us physicists is something which is clearly defined, or time or space. Of course, when you do string theory, think about space-time as some emergent object of some underlying complicated theories, then things are more fuzzy. But so I prefer, in this course, I will, I think, in the lecture, I will always keep in mind that that's an important but mathematical, analogy. Okay. So this is 1, 2, 3. Trying to organize my. Okay. So now let's. It's not working. So this one is not working. The front one seems not working. Okay. That's annoying because. Okay. I can hide behind, but it's a bit. Okay. Okay, so let's continue here. Then I will erase this one. Okay, so now let's go back to path integrals. So we go back here for this system. Okay, so you have seen that at real time, Feynman showed that at real time, matrix element of the evolution operator, which is defined here, that I'm going to define as in my lecture note K. So this is what is called the propagator, or the evolution operator matrix element. So I'm considering the matrix element of U of Tf minus T initial. So this is the evolution operator during time T, with initial state Qi and final state Qf, where Q is an eigenstate position eigenstate. So this is the quantum probability amplitudes for a particle for evolving from position Qi at time T high to position Tf, Qf at time Tf. So it's a probability amplitude. Okay? And Feynman showed that this object can be written as a path integral. So it can be written, well, this is the standard picture. So this is time. This is the time axis. This is the position axis. Maybe if you are here, you cannot read mine. So this is time. This is position. And at time T initial, your particle is at position Q initial. At time Tf, your particle is conditioned to be at position Qf. And Feynman showed that you can write this as an integral of a passes, Q of, let's call, since I have T here, let's call time, I label each time by the letter S. So S is arbitrary time, and T is restricted to initial and final time, of exponential of I over h bar times the action of, so you integrate over trajectories or histories with the constraint that at initial time, Q at T initial is Q initial, and Q at time Tf is Qf. And so you sum over all possible histories. So you have a sum of various histories. You sum over all possible histories, like that. And so this is a path integral. And here you have a phase factor associated to each history, which is the exponential of I times the action. And the action, in this case, what I call S of Q of S. This is a functional. This is integral from T initial to Tf of ds 1/2 of Q dot of S squared minus V of Q of S. Okay? So that's what Feynman showed. And I presume you have seen in quantum theory how this is derived, at least qualitatively, if not mathematically in a rigorous way. So the standard trick is to first show it for the free particle, the particle with no potential, where everything reduces to Gaussian integral, and decomposing. So the idea is to decompose this is small time steps delta t, and to show that this formula is valid at very short time, and then combine, by convoluting the different u's to get such a formula. So this formula can be proven as a limit when delta t goes to 0, so continuous time of an approximate path integral. So that's the idea. Okay. So, of course, this sometimes can be very complicated to compute, and sometimes it's easier than this. Yes?
You say S is a functional, and Q depends on what? Sorry.
It's a functional because it's depend on the function Q of S. So I should write this rather like that. So, because the action, it's already true in classical physics. The action is a function of the function Q of S along this. So it's not a function of one single variable or a finite set of variable. It's a function of functions in some specific space of functions that I'm not going to discuss here. But this can be, the mathematical theory of this exists, has been developed since more than 80 years or 70 years. So it's a functional is a function of functions, which to a function in some space of function, so a point in a space of function, it associates a number. Okay, so that's what's called a functional. Okay. Okay, so this is the standard Feynman path integral formalism. And the question I'm going to ask here is question: can this be generalized to Euclidean time? So, the question is the following. Now, I have my Euclidean axis time, remember? Remember, t is I tau, so tau is I t. So I am considering, I'm considering the evolution operator defined along this axis. And my question is, can I represent an Euclidean propagator? And I'm going to consider a simple case where, so my final Euclidean time is tau f, or let's call it, let me consider that tau initial is 0 and tau f, I call it tau, and it has to be positive, because it has to be on the real negative axis. So I'm considering q initial of qi, qf, and tau as just, so by definition, I just replace u by the Euclidean evolution operator. So I'm considering this qf, u Euclidean of tau, q initial. We have seen that this object is well defined because it's just a matrix element of the Euclidean evolution operator, which is well defined. This is well defined. And the question is, can we represent this as a path integral? Okay. And you can repeat the argument, well, the proof, the derivation of path integral by finding. So now what I'm going to do is that I have Euclidean time, so I have Euclidean time. So this is my initial Euclidean time 0. This is my final Euclidean time tau. This is the position axis. Okay? And I'm considering this object where the particle is at position qi at time tau 0, at q final at Euclidean time tau. Let me label Euclidean time, continuous Euclidean time by sigma. And the question is, can I write this as a path integral, as a sum over histories? Okay, so you can walk carefully and repeat the derivation of path integral, but in fact, the result is obtained by making just this change of variable everywhere in the formula. So you have seen that here, UE, you go from U of t to UE u Euclidean of tau by making this variable. So you can play by replacing that everywhere. So you replace real time S by Euclidean time sigma with a relation that S is minus I sigma everywhere. Okay? And you replace in your sum over histories Q of S, so function of the real time, by functions of Euclidean time. Okay? So you replace functions of time by functions of Euclidean time, where the relation is this. So in this case, you may ask, what becomes the action? The action S of a function of Q, which is integral dt 1/2, well, m over 2 dq over dt squared minus v of q. What does it becomes? Okay. I don't need that, so let me show you this. Okay. Well, first, dq over dt, so this is dq over ds, I'm sorry, because I'm integrating over the intermediate time. Okay. dq over ds becomes dq over minus I d sigma. So, dq over ds becomes 1 over minus I, so it becomes I dq over d sigma. Okay? Because I'm changing the variable in the differentiation. The line element in time, ds, becomes minus I d sigma. I'm just making a very naive change of variable. So this becomes, the actions becomes, so here I get a factor minus I times integral d sigma m over 2 dq over d sigma squared. Oh, and I have a I squared, so I get a minus which I can absorb here. And then I get plus v of q of sigma. So when I make this change of variable, the action of a function at real time becomes this object where I consider the function at imaginary time. So let me call this object, let me call it the Euclidean action of the function q of sigma. Okay? That's a definition. Okay? Then you see that formally the path integral becomes integral over all histories depending on some Euclidean time, sigma, times exponential So I had I over h bar times s, thus s becomes I s Euclidean. So I get minus 1 over h bar s Euclidean, the action associated to the Euclidean trajectory q of sigma. Okay, so this is an trajectory at Euclidean time. This is the Euclidean action. This is a path integral, but over path depending on Euclidean time. So we are summing over whole histories like that. We still have the boundary condition that q of 0 is q initial and q at time tau is q final. So we sum over all trajectories that start at q initial and ends up at q final. Okay, so this is a new path integral, but over trajectory as Euclidean time, at Euclidean time. And it turns out that this object, if you work out everything carefully, is precisely the Euclidean propagator between q initial and q final for the evolution during Euclidean time tau. Okay. And this is 1. It's not I. This is 1. So this is the Euclidean time version of Feynman path integral formulation, well, expression for matrix element of the evolution operator. Okay. So I have not been, I just make this change of variable, but you can work out things carefully, checking that at each step this makes sense. Okay. So this is a Feynman integral. And in fact, this is associated to name of a mathematician, Mark Cox, a famous mathematician. Okay. For this matrix element. Okay? And one important remark is that now the weight in the path integral associated to each trajectory, it's not a phase. Here it's a phase. Here it's a positive real number. So here, this is a positive real number. So it can be viewed as a probability. In fact, this formula tells you that, so it's a weight factor. So it means that in fact, at Euclidean time, what you are doing is statistical mechanics of a path. You are doing, we are doing statistics over random walks on the real line. Okay. No, this is time, Euclidean time. This is position, and so this each history describes, a a random walk of a particle as a function of Euclidean time that starts here and ends up here. So, in fact, this shows that there is a deep connection between Feynman path integral and the probability theory and the theory of random walks. And this is an analogy, a mathematical analogy, but which is very, very useful and has been used in statistical mechanics and in mathematics many, many times. So it's a deep mathematical analogy. Okay. Okay, so now let's go back to what we considered here, which was just on this, which is that the partition function. Let's go back to our quantum system. This was math. Now we are going back to physics, and we consider a quantum system at finite temperature. So our quantum system here, our particle on a line in a potential is in equilibrium with some big system which gives and takes energy to the particle everywhere, such a way that the system is thermalized and the particle is just moving in its potential weight, but it has some temperature. Okay? Then, well, everything somehow is contained in the partition function. The properties of the system are contained in the partition function. So what is the partition function? So this is Z of t. Well, remember the important relation which was written here that now it's hidden, that tau over h bar is 1 over Boltzmann constant times the temperature. So T is the temperature, and tau is the Euclidean time, corresponding some kind of Euclidean time. So Z of t is trace of exponential minus beta times the Hamiltonian. Okay. Of course, we can write the trace as a sum of the projection of diagonal elements of this operator. So we can write this as integral over the real line of dq, matrix element q, exponential of minus beta h q. Simply because I'm using the fact that the identity operator is integral over dq of qq. That's a decomposition of unity. Okay. So this is a way to write the trace in the basis of position eigenstates. Okay. But now, this is a particular case of the matrix element we have considered here. This is just integral over dq of u Euclidean of qq tau, with tau given by this relation between the temperature and tau. So, this is an integral over q of a path integral here, where the initial and the final states are equal and are given by q. So we consider path integral where initial and position are the same, and then we integrate over q. So basically what we do is that we integrate over all trajectory paths, all paths. So we can rewrite this as integral over all Q of sigma with exponential of -1 over h bar the Euclidean action for this trajectory. Okay? But now simply with the condition that Q initial is equal to Q final. So Z of t is just given by the partition function, is just given by this path integral. So this is the partition function. Okay? At temperature T. And this is a path integral, an Euclidean path integral, over periodic trajectories with period. Oh, I'm sorry, you are not able to read this if you are here. So the point is that the period here, the period is tau equal h bar over Boltzmann factor times the temperature. So you sum our trajectories, but the constraint is that the trajectory end up at the same point. So in some sense, you can repeat it. So you see that finite temperature. Now I think I can erase this. Finite temperature T can be described by a path integral at periodic Euclidean time with period tau equal h bar over kBt. Okay, so again, it's a mathematical correspondence, but it's deep. Okay, finally, let me go back. So I introduced what is quantum mechanics at Euclidean time. So now let me go back shortly to this denomination. Why Euclidean time? Why is it called? Okay, why Euclidean time? Why is this denomination? Well, in order to understand why this is used, we have to go a bit ahead of next lecture and go from quantum mechanics to quantum field theory. So think about now Minkowski spacetime. So in Minkowski spacetime, I don't have only time, but space. Okay. And there is a light cone, and the space-time Minkowski metric, d squared is minus dt squared plus dx squared. So here I'm using normalization that the speed of light is 1, and I'm using what's called the East Coast metric convention, which is that the signature of space-time is minus, plus, 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 and not plus, minus, minus, minus. Well, I'm used to that. I don't know if I feel closer from East Coast than from West Coast, but it's called that because many physicists on the East Coast use that, while many physicists in the West Coast use that. For instance, I think this is the one used in Weinberg. I'm not completely sure, but it's in some other books, while this one is normally the opposite choice is used in Peskin and also in other older books. Okay, so now think about making, going from real time to Euclidean time. So writing that t is minus I tau. Then the matrix becomes, of course, d tau squared plus dx squared. So our Euclidean space-time is tau and x, but this is just the Euclidean metric, so the metric of classical geometry in four-dimensional space-time. Okay, so tau is just an Euclidean coordinate, or let's call it Cartesian coordinate as the others ones. See? So, hence the domination. If we consider that time is imaginary and consider tau as a real variable, then space-time, which is Minkowski here, becomes Euclidean. Okay. And now if you think about, going back to this game, I wrote here, you see, it means that, in fact, so this is the realm of quantum field theory, and this is rather the realm of statistical mechanics. But through this, this change of variables, you can go from things you compute in a framework of statistical mechanics into things you want to compute in quantum field theory, quantum theory. And the trick is just to go from Euclidean time to real time. And most often you can do that easily because remember I stated, this looks a bit mathematical, that all the operators you are considering are well defined, but they are well defined as analytic functions. So you can go from real time to Euclidean time and back by analytic continuation. In time. And basically, also if this is real time, if this is Euclidean time, going from this to this and this is called a Wick rotation. And it depends in a crucial way in the fact that the evolution operator is analytic in the time coordinate. So this is a consequence of what's called analyticity in quantum field theory, which is very important properties of quantum field theory, which is a consequence of low quality and Lorentz invariance or Euclidean invariance. Yes?
But when we have a Minkowski metric, a Minkowski spacetime, we have a causal structure. And
yes.
when we big rotate, where does it go?
Well, the causal structure has disappeared.
Yeah, so isn't that a big problem?
Well, you can, for some specific object, like when you consider correlation functions in quantum field theory, I'm going to discuss that later. The fact that there is a causal structure, namely that the theory is unitary here, translate in properties of correlation function in Euclidean space-time, which are called reflection positivity. So there is mathematically something that corresponds to causal structure, namely unitarity here, but it's a mathematical property which is not completely, has no simple physical interpretation. But there is. But strictly speaking, of course, there is no, the light cone becomes just a point. Yeah. But that's a good question. Yeah, thank you. Okay, so I still have half an hour. No, I just have 12 minutes. So let me just hand up. I'm not going to talk about path integral, but I'm not going to talk about quantum field theory, but let me just go back. Okay. Let me just remind you. I think you have seen that also in the quantum theory course, but that's going to be important. So let me go back to quantum mechanics and to operators and what's called correlation functions. Okay, so that's, let's call 1.4. Because up to now, I've just discussed how you can formulate matrix element of the evolution operator in terms of path integral. But of course, quantum mechanics has to deal with matrix element of operators, observable, physical observable. And so, what is a dictionary for those? Well, the dictionary is quite simple. So let me just give a simple example. Where is it? Yeah. So we have seen that. The propagator, namely Q final, T final. Well, Q final, U of T final minus T initial times Q initial is given by a path integral. So now I'm going to write this in a very more sketchy way. This is a function with, so I just need to know that Q of T initial is Q initial and Q of T final is Q final. Okay, so this is a path integral. So I'm doing this path integral, T initial, T final, Q initial, Q final, and this we integrate over those passes. Okay? So this is a notation in the Heisenberg picture. But if you go from Heisenberg to Schrödinger, to Schrödinger. But if you go from Schrödinger picture to Heisenberg picture, I presume you have seen that in the quantum theory course. This matrix element is nothing but notation QFTF times Q initial T initial, where the state Q initial T initial is just Q high times U dagger of T high. And the same for Q final of T final is U dagger of T final, Q final. And then this absorbs the U's in the matrix element. Okay. So this is the states where at time Ti, the particular position Qi, and this is the state where at time Tf, Q is a position. Okay. So now we can ask question. What happens if I insert something here? I'm interested at some position T1 here. T1 between Q initial and T initial and T final. What happens if I measure the position of the particle? I measure in the sense that I insert it in the integral. So what is this functional integral? D of Q exponential of I over h bar, the action for the trajectory, times Q at time T1. What is this object? With the same boundary conditions. So, same boundary conditions. Okay. Well, it's easy to understand what is it because in this integral over histories, we can fix that Q at time T1 is some Q1. So we can write this as integral dQ1 times a path integral where the position at time T initial is at Qi, at time T1 it is at Q1, and times a path integral where at time T1 it is at Q1 and at time Tf it is at Qf. You see? Times Q of T1. So this is Q of T1 times this matrix element. So first I have this, which is Q1 U of T1 minus T initial times Q initial. This is the contribution in the path integral of this. And the contribution of the path integral here is the matrix element Q final U of T final minus T1 Q1. And this is Q1, simply. Because I fix this Q1. Okay. So now, insert this Q1 here. This is Q1 again, I'm sorry. So this is a contribution of this. And this is the contribution. Not the right color of this. Okay. So you see that Q1 here is just a dummy integral, a dummy variable we integrate over. So what is integral dQ1? So I have the ket Q1 times Q1 times the bra Q1. You see, it's a linear combination of projection operator. But remember, Q1 is the eigenvalue, is one eigenvalue of the projection operator, of the operator Q, with eigenvector is Q1. So this is just the operator Q, position operator. this is an operator. Because this is the eigenvector of Q with eigenvalue Q1. Okay, so this is just the position operator. And therefore, this can be rewritten simply as a matrix element between QF and Q initial of the evolution operator between T1, between T initial and T1. Here I have Q. And here I have the evolution operator U between T1 and T final. Okay? So, this, here is my red. This is just this matrix element. It's a matrix element where you combine evolution operator with the position operator itself, the quantum operator. This is an operator. Okay. And this is, of course, an object described in Schrödinger picture, but if you can rewrite this in Heisenberg picture, it's an exercise to show that this is nothing but the matrix element between QF, the states QF TF, and the states Q initial T initial of the operator Q applied at time T1. Remember, in Schrödinger picture, in the Heisenberg picture, operators depend on time. Okay? So, inserting Q of T inside the path integral, amounts to compute matrix element of the corresponding operator Q. So you see that the classical correspondence principle in canonical quantization between classical functions and quantum operators holds also here for the position operator. So this is, Q of T, which is a random variable in the path integral formalism, because you integrate over something that can take all value possible, equals the operator Q of T, which is a quantum operator in Heisenberg picture. So you have a similar correspondence principle between classical variable and quantum operators in the path integral formalism. Okay. And finally, if you give me 2 minutes, next step. Two operators. This is front. So what is the same integral? Path integral, exponential I over h bar, the action of the trajectory with the same boundary condition where I insert Q at time T1 and Q at time T2. So instead of having T1, I have here T2. Well, you can repeat the operation. It's quite trivial. You decompose this times this times this. And what do you get? So this is T initial, T final, T1, T2. And here, Q1, Q2, and I integrate over Q1 and Q2. This is Q initial, final. And well, it's a simple exercise to see that this is equal to, well, usually the eigendifferential is the matrix element between Q at Q at over Q and T2 times Q at T1. Because first you evolve, then you apply Q and T1, then you evolve, then you apply Q at T2. And then you evolve. So this is equal to this. But of course, if T1 is less than T2, and between T initial and T final. See? If we are in this situation where T1 is larger than T2, it's just interchange the role. So of course, what we get is the same matrix element here, initial, but Q at time T2 has to be applied before Q at time T1. If T2 less than T1, less than T1. So easy. So this path interval, where Q of T1 and Q of T2, the considered and unknown variables are just numbers in the commute, gives matrix elements of two operators which do not commute. Because remember, Q in the Eigendorf picture is a combination of Q and U by combination operator, and Q doesn't commute with U. Okay. And so you see that the path integral, basically the conclusion is that path integral automatically gives time order products of operators. Automatically, Q at smaller time are applied to state before Q at larger time. So basically, with this path integral, we have integrate exponential of minus S Q of T1 Q of T2 construct matrix element of the time order product of Q of T1 Q of T2. And this time order product is defined by a big T. So by definition, T time order product of Q of T1 Q of T2 is Q of T2 Q of T1 if T1 is less than T2, and Q of T1 and Q of T2 if T2 is less than T1. That's the definition of time order products operators. So although those random variables are numbers that commutes, path integral take care of the causal structure of quantum mechanics. And if you work that a little bit, you can show that you can obtain from path integral the commutation relation of P and Q. I want that to discuss that today. Maybe I can come back to that. That's all causal structure.